think we are on here. Okay. So, a quick summary of last class. You remember we presented the Lorentz model. Okay, so very briefly, remember we described the classical electron oscillator model. Remember equation of motion. So if you write it for the dipole moment, so we look at all the atoms as individual dipoles, and we wrote this equation here, which gives you the time variation of the amplitude of the dipole moment as function of time, okay, with two terms. One gives you the natural oscillation of the dipole at the resonant frequency omega A, and the second term here is the damping term, where gamma is described the energy decay rate of the system. So it's really a spring mass oscillator with some damping element. And we have this expression for omega A in presence of gamma, which is roughly omega A, the resonance frequency of the dipole. And you remember we equated this frequency for the dipole to the frequency which corresponds to the transition between level 1 and level 2, omega 1, 2, which is E2 minus E1 over h bar. Okay, so by analogy between the classical oscillator and the atomic structure, we made a direct correlation between omega A and omega 1, 2. Okay. As far for gamma, for the decay rate, which usually has two components, a radiative component and a non-radiative component, we have an expression here for the radiative part, okay, in terms of omega A and some constants. Okay, this will be derived today in the exercise class, I think. Okay, so we have this expression. So you remember we started from this microscopic description, atom by atom, and then we go and we move from microscopic to macroscopic description. So from dipole moments to microscopic electric polarization, P, which is a sum over all these small polarization of all the atoms. Okay. So you remember that this introduces a new source of damping inside the system. Why? Because all these oscillators that are not necessarily in phase, and that's especially happens when you have collision. Because of collision, you introduce dephasing between different oscillators, and that will sum up destructively, and it will reduce the amplitude of the polarization. So that's what I could not draw last time. Okay, so you see for three atoms in phase, when you have a collision here, you introduce dephasing, so automatically the sum here is not maximal, so you reduce the amplitude. Then you have a second collision here for the second atom, and you reduce a little more the amplitude. And statistically this will decay, and the typical decay is called T2. T2 is the dephasing time, which measure the mean time between two collisions. Okay? So the overall decay rate is the sum of the radiative decay rate gamma, the damping term, which includes the radiative and non-radiative terms, plus 1 over T2 here, which represents the collision decay due to the fact that we consider an ensemble of dipoles. Okay, so that's what we presented in the first part last time. Okay, so you remember this equation, the equation of motion. If you don't if you leave out the second term, if it's a system without external excitation, you solve it and you find a decaying, exponentially decaying signal, okay, with the time constant, which is given by this term, okay, which includes all the mechanisms that induce losses or decay inside the system, okay. Now, if you take the full equation now with the second term, so let's say we excite the system with an external field, E of omega, the given frequency omega, okay? So if we excite the system at that frequency, then it's more difficult to solve the equation. What we did last time was to solve the equation for the steady state, okay? When the system reaches the steady state. So at omega, what we learned last time is that an external field will transfer energy into the system by inducing a polarization, okay? So the induced polarization will also oscillate at omega, okay? And there is a linear relation, which is given by this expression, and K here is the susceptibility, which is actually it is a tensor, so this is a vectorial expression, but let's simplify it, okay, and put everything in the expression of K here to take into account all the different aspects, okay? Just a remark, this is a linear relation. Actually, there are other terms further for higher power of the electric field, which are nonlinear terms. Okay, so when you deal with nonlinear optics, you don't stop at this expression, but you look at the successive term in a kind of Taylor expansion, okay, in terms of E squared, E cubed, okay, which are much smaller terms, but which are nonlinear terms that describe actually the interaction between the light and the matter inside the system. So that was a small remark. Okay, so we wrote the expression for chi here for the susceptibility. Forget about this atom here. So it's a complex number, and it depends on omega, and it has a real part and an imaginary part. And we can write it in a very simple way here. So there is an amplitude for the susceptibility here, and two terms here, which are two functions. This function is called a Lorentzian, a complex Lorentzian. The real part here is the blue line here as function of frequency. So delta x is the difference between omega and omega a. So I excite the system at omega. The system is naturally resonant at omega a. So if you are far away from omega a, at omega, you will have almost no interaction between the field and the medium. If you get closer to omega a, if omega is close to omega a, then you start to see some effect here. That's for the real part, and for the imaginary part, it's this curve here, which gives you actually the amplitude, the true amplitude of the interaction, okay? And chi 0 prime here is given by this expression that we calculated last time. And delta omega A here, so this is the line width of the transition. So the line width here at half maximum is given by this expression, which is exactly actually the damping factor when you solve the equation with the homogeneous equation without the external field, okay? So it means what? It means that if I excite the system at a given frequency omega, okay, it will be the process, the transfer of energy will be more or less efficient depending on where I am on this plot and what type of Lorentzian curve I have here for chi, the transfer function chi, okay? So I think that's it. I just show here a measurement. You can measure a spectrum emitted by some system, some optical spectrum here. So this is the red curve you see here. You can measure it, and you can say, okay, this system is made of many resonances, so I can fit the data with a sum of Lorentzian. Okay, and this is what is done here. So you have one Lorentzian blue here, the green one here, the purple one here, and when you sum them up, you get the black curve, which fits quite nicely the data. Okay, so this is a good, let's say, a good description actually of resonance system in terms of Lorentzian line shape for a resonance. Okay, and maybe to finish this review. Yes. So you remember the idea was to make some kind of equivalence between the classical model and the quantum model, the atomic system. Okay, so omega A becomes omega 1, 2, the frequency transition. What else? Yes, the population, you remember, you have to replace the population by delta n. Population inversion, delta n is n1 minus n2 here. And you end up with this equation for the polarization. This is the complete equation, okay? So it has this homogeneous part, which corresponds to the oscillator, and this part here, which depends on the field, okay? The external field, and the population inversion inside the system. Both of them are time-dependent function. Okay, if the population evolves slowly, you can forget about the time dependence of delta n. This is called the rate equation, the rate equation approximation. Okay, what else? You remember this factor 3 star here, which can be between 0 and 3, depending on the alignment of the field with the dipoles, and if the dipoles are all oriented or not. If everything is aligned, so the transfer of energy will be the most efficient, so this term will be maximum. Okay, so all the tensorial description is embedded in this number here. It's a simplification, but it is quite useful. Okay, and so that's for the polarization, and the expression for the for the susceptibility here, again, is given by the Lorentzian. You see that, oh yes, there is one thing that we did also, was to replace the susceptibility amplitude, the chi 0 prime prime, okay? We replaced it by gamma radiative, the expression that I gave at the beginning, I recalled at the beginning. Okay, so be careful here. In this expression, this is gamma radiative. Okay, delta omega here is gamma, not gamma radiative, full gamma plus 2 over T2 for the line width. I think that's all. Just for the next. Okay, so we did not finish completely this chapter. I'm going to finish it now. Just some drawing here that I will not be able to do it myself, so let's look at that. You have two main type of curves here. So the Lorentzian is the blue one. So that's the Lorentzian shape, the Lorentzian line shape. So quite narrow. Okay, it goes very fast to 0. Compared to the Gaussian here, which is the black curve. So the Gaussian curve is more like a bell curve. Okay, and if you have a function which is a mixture of the two of them, you get this kind of green curve, which is like in between the Gaussian and the Lorentzian. So keep that in mind. Up to now, we discussed resonances with the line shape, which is Lorentzian. I just want to show you that it's not always the case. Okay, and in some situation we see that you go from Lorentzian to Gaussian shape. Okay, but that's okay. Instead of giving the line width of the Lorentzian, you give the line width of the Gaussian, and you can use the same tools for the description of the susceptibility and the transfer of energy from outside to the system. Okay, so okay, so what I miss in this chapter is the last paragraph. I want to discuss line-broadening, by the way. So line broadening, the fact that you have a line width with the line width is given by the mechanism involved. So I want to describe that. I think it's very interesting physics. And actually, this is something which is very important to understand the physics of lasers. And the idea is like that. If you consider that all the atoms in the system, they have the same line shape, okay? So a Lorentzian center has the same omega A and with the same line width, okay? So they are all the same type of atoms. So globally, if you look at the full system, it will have what we call a homogeneous broadening, okay? And typically the broadening is given by this delta omega A, which includes gamma, the damping factor, and 1/T2, okay, which is the collision rate inside the system, okay? So that's the case where everyone is the same. They all look like the same, and they behave the same way. So homogeneously, everyone will respond the same way to an external excitation. Now, if for some reason all the atoms, they don't have the same, let's say the same central, the same frequency of oscillation omega A. So there are some fluctuation, okay? So instead of a Lorentzian shape, you will have like a sum of Lorentzian shape, okay, with some shift in frequency, because from one atom to another atom, you'll have a different omega A, a different central frequency of the line shape, okay? So this will completely change the picture and the shape, the global shape of the response of the system to an external excitation. And in the case where you have very large differences, very large shifts between different atoms in the central frequency, so that will completely change the picture, and we'll go from a Lorentzian line shape to a Gaussian line shape. Okay, and I want to show that to you, to demonstrate that to you today. To close this chapter on the Lorentz model. Any question? I'm sure that you review all that and you have everything in mind. Yes, we can continue. I really want you to understand the physics here. I really want you to understand what we are doing. We are considering the excitation from an external field at omega, and we want to see how the system reacts, how the system stores the energy brought from outside, okay? And this is given by this relation that we discussed. This part more illustrated. I want to take an example. So we are going to consider the helium-neon laser. So those who are in the lab, they know what I'm talking about, and this is a very familiar laser that are used in all optics lab. So this is the last part of the chapter. It's I think it's number 6. So this was line-broadening mechanisms. So we will consider two classes of broadening. We'll have homogeneous broadening and inhomogeneous. Okay. First case, all the atoms they behave the same. They have the same response to any external excitation. In the second case, there will be some differences. Okay. So the question: what are the mechanisms responsible for either homogeneous broadening or inhomogeneous broadening? And we are going to consider the case of the HeNe laser, helium-neon laser. We'll get a chance to discuss that in more detail, but just the line width, the typical line width of this laser is typically 1.5 gigahertz. Okay? So if you look at the fluorescence of the atomic transition, you'll see a line width which is about 1.5 gigahertz. Okay. So the question is, what mechanism is responsible for this line width? So let's start. So the first one that you know is called lifetime broadening. So what is responsible for that? This is the gamma term, okay, which describes the lifetime of the transition from level 2 to level 1, okay. So this is gamma, which is composed of gamma radiative and gamma non-radiative, okay. And the longer the lifetime of the transition, the narrower will be the line width of the spectrum. Okay. So this case will have, I mean, all atoms have the same decay rate, the same lifetime. Okay. So this is the case of homogeneous. I call that homogeneous broadening. This is IB. Okay, so this is a case of homogeneous broadening. Typically for the case.
What the NR represent?
Here?
Yeah.
Gamma radiative and gamma non-radiative. Okay. So typically for the HINI, laser, gamma radiative is about 10 to the power 8 7 minus 1 or hertz. Okay, so that gives you a frequency. So delta omega A over 2 pi is about tens of megahertz. Okay. So that's typical for a gas laser. This is the typical decay rate. Yes?
The width, it means that the light of the laser, it's not coherent.
The line width?
Yeah, the width, it means that the light is not coherent.
No, it is coherent.
So what does it represent?
That's okay. At this point, what we understand here, it represents the efficiency of the conversion from an external field into the atomic system. Okay. At this point, that's what we discussed until now. Okay. So this is P equal epsilon chi E. Okay. But this represents at the same time. We'll discuss that. It represents the fluorescence of the system. The photons that are emitted by the system spontaneously. Okay. So you see here in that case, so if the broadening is due only to the lifetime of the transition, that's why you get the narrowest line width. Okay. And this is very small here, 10 megahertz compared to 1.5 gigahertz. This is probably not. This is for sure not the source of the line width of the transition for the HINI laser. So that's the first mechanism that you may consider. The second mechanism, you know what it is, it's due to collision, okay? Once you have collision, you are going to broaden the line shape, okay? And, okay, so this is due to this T2 collision time, and we call that pressure broadening. Okay. Why? Because when you increase the pressure inside the cell, the gas cell, you increase the chance for collision between the atoms. Okay. So for sure, as you increase pressure, you are going to broaden the line width of the system, and And typically the way it works, it's delta omega A. So delta omega A, which is gamma plus 2 over T2. Okay. You can, so as a function of the pressure inside the gas, you can write it as a linear function of the pressure, A plus B times the pressure. So times the pressure inside the system. So as you increase the pressure, you increase the broadening due to this term here. A and B are just constant, okay, so it's a simplification. And it will depend on the nature of the gas and the geometry of the system. So what is the degree of line width broadening due to pressure in the Heine laser? So here we consider the line at 632.8 nanometer, and the line width is about 70 megahertz per torr. Okay, so torr is a unit for pressure. Typical pressure in the Heine laser is about 2-3 torrs. Okay, so we are around 100 of megahertz for the line width broadening due to collision. Okay, so that's not enough. Okay, we are still far from 1.5 gigahertz. Okay.
Can you explain torr again?
Sorry?
Can you explain what torr is again?
Torr is a unit for pressure,
Oh,
like
okay.
Pascal. Okay.
Okay.
So now, don't ask me what is the exact relation. That's typical in this context. So we need something more efficient for line shape broadening. Any suggestion? Any idea? So I should mention here that this pressure broadening is also a homogeneous broadening mechanism. Okay, it's HB, homogeneous broadening mechanism. And obviously it's not strong enough to explain the line width here. Any suggestion? No? So think about a non-homogeneous, inhomogeneous mechanism that could happen in a gas. So do you think that all the atoms in the gas will have the same oscillation frequency, the same resonant frequency, or not?
It depends on the mass. It depends on several variables.
No, let's say that all the atoms, they are identical, okay? They are all identical. But it's a gas, okay? So they are moving around inside the system. There is a Brownian motion of the atoms, okay? In principle, if you take each atom individually and you look at it separately, they all have the same line width, okay? But they are moving one relative to the other, okay? So what happens when you are in your car and there is a car in the other direction?
Collision?
No, I'm not. No, so the guy is just using his horn and you pass by in the other direction. What do you hear? Yeah, you hear what is called Doppler effect. Okay, so this is an artificial change of frequency. Okay, but it's there. Okay, so you have moving particles, and as they cross, one is seeing a particle with a different resonant frequency just because they are moving one relative to the other. Okay. So this is called the Doppler broadening. This is something that we can calculate, actually, that we are going to calculate here. So let's see here. Doppler broadening. So this is due to the fact that we have the distribution of velocities inside the system, okay? This is given usually by the Maxwell-Boltzmann distribution function of velocities. And because of the Doppler effect, the atom, they experience a shift in frequency. Okay. So now, if you look from the lab, okay, you have actually many atoms, but for different central frequencies, so a different line shape shifted in frequency. Okay, this is typical of inhomogeneous broadening. This is the main mechanism that can produce this type of broadening. Okay, so let's try to calculate that and to see if we can get the true line shape and if we can explain this large line shape here. Okay, so let's say you have an atom at frequency omega A, okay, with a velocity v. Okay, so from outside what you see is not anymore an atom at frequency omega A, but an atom at frequency omega A prime. And the direct relation between omega A and omega A prime is omega A prime is omega A times 1 plus V over C. Okay. So this gives you an idea of the shift, the frequency shift. So if you have very fast particles, this term is significant. Okay. You can rewrite this expression in a different way. You can write it like that: omega A prime minus omega A over omega A is equal to V over C. Okay, and we are going to use that expression here. Okay, here I simplify completely the problem. Let's say everything is moving along one axis. Okay. And you have velocities in that direction, okay? We are not considering the projection in the three-dimensional space, just to simplify things. That's why I write it like that, okay? And now what we have is a distribution of velocities, because we have a Brownian motion inside the system, and typically the Maxwell-Boltzmann distribution Maxwell-Boltzmann distribution gives you P of V dV is square root of m over 2 pi k t times exponential minus m v square over 2 kt dv. Okay, so that's well known. So it's what it is. This is a Gaussian distribution around v equals 0. This is v. It's a Gaussian distribution. And we're going to use that. So the idea of the exercise here is to go from this probability distribution of the velocity of the speed, okay, to go from this to omega A, the distribution of resonance frequencies, using this expression, okay. So it's very simple. You just replace V here by this expression, and you replace dV also by differentiating this equation, okay. So omega A here is fixed. This is the absolute resonant frequency, and omega A prime is distributed in the frequency space, okay, as you experience atoms with different velocities, okay. So if you transfer, so if you you do the change of variable here, you get P of omega A d omega A is equal to square root of m over 2 pi. K is the Boltzmann constant, and T is the temperature. Okay, exponential of minus m v square given by that, so it's omega prime a minus omega a over omega a square over so there is mc2 here, mc2. What else? Over 2kt dv. Okay, dv is in here. So let's put d omega a c times d omega a prime. So this is what you obtain by changing the variables. Okay.
But
I forgot something.
Question. We are using the non-relativistic Doppler effect, right?
Say that.
We are using the non-relativistic Doppler effect, right?
Yes, yes.
But
That's simplified.
we are using like high speeds in a laser.
No, we are talking about atoms in the gas. Typically, they are not that fast. Depends on the temperature, but it's not relativistic for sure. Okay. So here we are talking about the motion of the atoms within the gas. Okay. So I can rewrite the expression in a more nicer way. Let's say so. P of omega a prime d omega a prime is equal to okay, I give you the expression 4 log of 2 over I delta omega d. So I introduce here a new line width. Okay, we have delta omega a here. Where is it? Delta omega a will be related to that. Okay, so it's delta omega d. That's the new line width introduced here. What else? This is squared times exponential of minus 4 log of 2, don't worry over the constant, times omega prime a minus omega a over omega delta omega d, everything squared, d of omega a prime. Okay? So this part here, this expression here, is what is the probability density of atoms with the resonance between omega a prime and omega a prime plus delta omega a. Okay? I write it. So this is the density, the probability density. Probability density of atoms with frequency omega between omega a and omega a prime plus delta plus d omega a prime. Okay. So that's the distribution that we obtain. And the expression for delta omega d is omega a square root of 8 log of 2 kt over mc square. Okay, this is a typical exercise that we can ask you to reproduce. So omega d here will be the new line width. So let's see what we can do with this probability density. I'm going to erase this part here. So now you have to realize that for each group of atoms like that, okay, we have like a new line width, okay, and somehow one is different from the other, okay. So they have to be summed up to describe the susceptibility. So if I want to write the total susceptibility chi of omega, I will write it like that. It will be a sum from minus infinity to plus infinity here of, let's say, the susceptibility, the homogeneous susceptibility of this group of atoms. Let's say a group of atoms between omega A and omega A plus d omega A have roughly an homogeneous line width. Okay, so I call that chi h of omega A prime, and times this distribution here p of omega A prime d omega A prime. Okay, you see what I'm doing here? So I have, if I look at the spectrum and I want to draw this chi function at for each given frequency, I can say that I have an homogeneous line width. Okay. Next one will give you another homogeneous line width here. Next group of atoms, another one. Okay. And you sum all that, and then at the end you will have a sum which gives you the total chi of omega. Okay. With the line width here, the total line width here, given by delta omega d, while the small one here is delta omega A. Okay? So that's the idea. Okay, you follow me? It's okay? A question? Any question? It's clear? So you see, the idea is that to say that for atoms which are very close to each other in terms of central frequency, I can consider that as a homogeneous line width, individual homogeneous line width, and I will sum them. Actually, it's an incoherent sum of chi of omega to get the global line shape of the susceptibility, and the result is the following. You get chi of omega is, I write the full expression here, minus I 3 star over 4 pi squared times square root of 4 log of 2 over pi. So that's the constant, only that. Then you have delta n times lambda AQ times gamma radiative over delta omega A times delta omega D. So that's the constant term here. And all these times the integral, which is quite complicated. It's an integral from minus infinity to plus infinity of the following function, exponential minus 4 log of 2. So this is the term here. Omega prime A prime minus omega over omega A, over pi. There is a pi here. Maybe I forgot a pi here. I may have forgot a pi. I delta omega d square over 1 plus 2i omega minus omega prime A over delta omega A. Sorry. Okay, so I'm just using the expression that we wrote before for the homogeneous susceptibility times the probability distribution here. I'm guess I'm missing a pi here to be checked. Okay, and so I'm not solving this integral. Okay, it's too complicated to solve it directly like that. So there is nothing new here. Just be careful to the constant term, but that's okay. So what do we do with this expression? Okay, so this is the analytical formula. What you can say here is, I mean, you can make some approximation depending on the situation. If delta omega A is much larger than delta omega D, okay. So in that case, you end up here with the, so it's delta omega D. Sorry, I wanted to say the opposite. Delta omega A. No, that's okay. Delta omega A larger than delta omega D. Okay. Then this expression here is a delta function actually. So if this is a delta function with the integral, you just end up with this expression, which is the Lorentzian, okay, which is the Lorentzian due to the homogeneous broadening. So in that case, you get a Lorentzian shape. Okay, so if delta omega D is small in front of delta omega A, that means that we have very small fluctuation in omega A. So roughly, you recover the Lorentzian shape. And if you look at the other extreme, delta omega A much smaller than delta omega D. So this is what I draw here. You see a small delta omega A compared to the delta omega D here. So in that case, if you look here, so this term will go to zero actually. Actually, yeah, you end up with this term exactly here, which gives you a Gaussian shape. Okay, so that's what I show you, these two different line shapes before on the screen. And in between these two, when you are in a case where delta omega A and delta omega D are comparable, so you'll have a convolution of the two of them. And this is called the Voigt, V-O-I-G-H-T line shape. Okay, so it's a kind of intermediate line shape between Gaussian and Lorentzian. So can we answer the question now about the Heine? And actually, if you put numbers in the expression of delta omega D, you find that for the Heine laser, delta omega D over 2 pi is of the order of 1.5 gigahertz. Okay, so I don't do the numerical application, but you can check it. So now we can answer the question. The line width here is essentially due to the Doppler broadening, to the fact that we have a gas, the atoms are moving around, and it's an inhomogeneous broadening in that case, in the case of the crystal of the gas. And this is the main source, the main reason for the broadening of the line shape for the Heine transition. Okay? Any question?
When you want to broaden the line in the first place, does it mean that it will have more frequencies than? Why do you want to broaden the line
this
We
line
don't
in
want
the
to
first
do that.
place?
We would like to have a very narrow
Oh, okay.
line, but the physics, I mean the physics of the system that you consider
So basically,
will broaden it naturally.
so basically, the thinner the line is, the more coherent the.
No, but the stronger the effect. Remember that the line width goes like delta omega A, and the height, the maximum goes like 1 over delta omega A.
Okay.
So the narrower, the stronger will be the transition. Okay, the more efficient will be the transition. So all these effects are not good actually for laser.
If I want to make the laser more ideal, so I only have to deal with the problem of the Doppler effect. So
Doppler effect, and if you can also reduce condition.
no, but it's a 1.5 gigahertz compared
In that case, yes.
to. So all that I have to do is just give them reverse Doppler effect. So and I don't care about collisions at all.
Right. No, just cool down your laser. Instead of room temperature, you work at nitrogen temperature. You will improve the efficiency of your laser. Simply like that. So in the following, for all the other classes, when I will speak about line shape and I will consider Lorentzian line shape, I mean you can transpose and say, okay, in the case where we have Doppler broadening, just replace the delta omega A line width of the line shape by delta omega D, the line width of the line shape for this case where you have a lot of Doppler broadening. Okay. In solid, it's more difficult to find. Most of the effects are related to lifetime broadening and to this T2 here due to interaction with the matrix. So you have like atoms that are embedded in a crystal, in a matrix, and the vibration of the matrix interacts with the atoms. So the case where you may have the equivalent of Doppler broadening for a solid is the case where the matrix, the crystal, is not homogeneous. That means that an atom here will feel an environment which is different from an atom here or there. Okay, so all these atoms they will not have the same resonant frequency or the transition frequency because of the environment. Okay, so but usually a crystal is something that is quite homogeneous and uniform.
This is why we use it on lasers?
Yes, no, we use Heine lasers. I mean, you know that we use it.
No, of course, but I ask specific on why we put crystals inside laser, because their structure is homogeneous. Scale maybe?
Mostly because, yeah, as a great medium, mostly because they are more efficient in terms of emission. The transition are much stronger.
And why I can't take just glass that have a red paint or green color beside it?
So the green color that you mentioned is the fact that the glass is doped with some ions, some other atoms or ions, okay, which are fluorescent. Yes, sure, you can have. I mean, if the fluorescence is efficient, then yes, you may make a laser with that. Okay. So here we are not yet into the laser. We are talking about the diatomic system that will serve as the gain medium, and you want to optimize the gain medium to get as much as possible interaction between the photon that will travel inside your laser and the gain medium. Okay. So here we see how we can optimize the gain efficiency within the gain medium. Just to finish this chapter, or maybe just a few examples. What do we have here? It was on the presentation. I have example of different type of lasers. The YAG laser, the lag laser, it's homogeneous. Okay, it's a solid. All the solid laser mostly they are homogeneous. And the gas laser, you have the Hini laser, the argon laser, which is also inhomogeneous. But for instance, the CO2 laser, which is also gas laser, is a homogeneous broaden laser. For liquids like rhodamine, so what we call dye lasers, usually they are homogeneous broadening. The case which is ambiguous is the case of semiconductor lasers, so laser diodes. Okay, it's not clear. Sometimes it's homogeneous, sometimes it's not. It depends on the type of semiconductor that is used and the structure of the laser. Okay, and I just want to finish by to add two points to make the story more general. Can I erase here? The first point I want to make is very easy. We are talking about one transition between level 1 and level 2. In general, atomic systems are more complicated than that. So there is not only one transition between two levels, but you may have many transitions. Okay, so between levels I and J, I being 1 to N and J 1 to M. Okay, so you may have many transitions. So simply the idea is to take them separately. Okay, each transition will have its own frequency transition, omega AJ. Okay, so if I have a general transition between level A and J, so we consider omega IJ. Okay, and for all different transitions, I will have different omega AJ. I will have also different delta N. I will consider delta N AG, the population inversion, the gamma. The radiative decay will be also gamma AJ. This is very simple to understand. You just have to adjust to the transition. The delta omega A will be also indexed like that with AJ. Okay, so it's very easy. In principle, it's quite easy to consider a multi-level atomic structure by considering separately all the transitions. Okay, some transition will dominate, other will be very weak, and then you can make approximation, and that's the way people deal with what you really find in nature. In nature, you never find a two-level atomic structure, a very simple one. It's already much more complex. And the final generalization that I want to make is the fact that instead of having many levels and many transitions, you may have what is called degeneracy. That means that you may have a different transition between two levels. So you may have two levels like that. So for degeneracy, you may have, let's say, two lower levels at the same frequency, and like at the second level here, you may have like two degenerate possibilities. Okay, so depending on the polarization, you may jump from this guy to this one, or you may go from this one to that one. Okay, or this one to here. Okay, so you may have all the combination, but here we only have two levels. Okay, and this is also something which is very common in nature, is to have degenerate states, degenerate levels. Okay, how to deal with that? So let's say that we have here G1 number of degenerate states, and here we have G2. Okay, how do you generalize what we discussed? You just write that delta n. So what you do here is that in principle you sum all the susceptibilities. Okay, susceptibilities will have the same omega A and the same delta omega A, but there are many possibilities, many combinations here. So you just have to sum them. So you sum the susceptibilities. That's one point. So chi is the sum of all the chi index k. Okay, and always replace delta n, which we wrote n1 minus n2, is replaced by delta n equal g2 over g1 n1 minus n2. Okay, so this is just to keep in mind. I don't demonstrate anything here. I just tell you the trick. The trick is that instead of n1 minus n2, you consider g2 over g1 n1 minus n2 to take into account the fact that you have multi levels, multi states at the same level, on the ground level and the excited level. So you remember the condition to have population inversion is what? Is delta n should be larger than 0, and delta n should be smaller than 0, and 2, population in level 2 should be larger than population in level 1. Okay, so in that case here, where it's more complicated, the condition will be the same. Delta n should be less than 0, which means that n1 over g1 should be less than n2 over g2. And it makes sense, okay? You have to consider the fact that you have multi-states at level 2 and multi-state at level 1. So the condition for population inversion is n1 over g1 be less than n2 over g2. Now you understand why I write it like that, delta n less than 0. Okay, see, this is not very important. This is just to tell you that you can generalize the description that we made until now to more complex system, multi-level system, or degenerate system, and it's quite simple to introduce this complication. So we are now in the middle of this long story I'm trying to tell. So I think it's very interesting because it starts from a very simple model, this Lorentz model, this classical oscillator, and we start to develop the concept and the model, and we learn up to now how an external field can transfer energy into a given system. Okay, so we have a first description of light and matter interaction in the system. So as we review that, the electric field induces inside the system a polarization, and all the atomic collection start to oscillate in response to this field. And if you remember, one of the parameters there, you remember this equation, this long equation on the polarization. On this side, you have the field. So obviously, it depends on the intensity of the incident field. But there was also delta n. Okay, so it depends on the population difference within the atomic structure. Some atoms will be excited, others will be in the ground state. So this difference of energy is an important term. The transfer of energy from outside into the inside of the atom depends on delta n. You have that in mind? Okay? You remember the term on the right side, delta n times delta n of t times E of t? So it's very important that there should be a population difference within the atomic structure for the energy to be transferred. So that's one time, okay? But if you remember what we discussed in the first chapter, the first course, we discussed what we call the stimulated transition, stimulated absorption, and stimulated emission. And in that case, there was also an external field, an electric field. But the effect of this field was not to bring energy, but to change the population. Okay? okay, we have a transfer of atoms from population 1, from level 1 to level 2, or in the other direction, from level 2 to level 1. Okay, so on one side, we see that an external field has induced polarization proportional to delta N. On the other side, we saw before that an external field plays the game of transferring atoms from level 1 to 2 or from 2 to 1. Okay, so it's completely two different processes, okay, but with the same external field. So, you follow me? Yes? No? Not really? So just have in mind these two mechanisms. The one that we described up to now in this Lorentz model is proportional to delta N, the difference of population. What we described the first lesson was a transfer of energy by a change in the population distribution from level 1 to level 2 and reciprocally. Okay? So I want here, we are going to try to, so we have like two different pictures and it's hard to understand how it works. I mean, is it delta N that is changed or is it the N1 versus N2? And we need to somehow bring together these two pictures, these two effects. And that's what we're going to do here by discussing what we call the rate equation. So this is lesson 3. So it is about atomic rate equation. I always keep the title from the book, from the Sigma book. So if you want to go back to the textbook, you know to which chapter you can refer to. And I want to start first by continuing actually the classical description by calculating the power that one can transfer from the external signal, from the optical signal, to the atoms. Okay? Okay, we describe this chi susceptibility, which relate the external field and the polarization. Let's talk quantitatively what is the power transfer in this process. Okay, and I will do a quite simple calculation, which is based on mechanics. Okay, so mechanical interpretation. That's what I will do. There is a different approach, which is an electromagnetic interpretation. Electromagnetic. Okay, this I will not address here. This is in the Sigma book if you want to have a look. It's page 178. I will just focus on the first one here. Okay? So let's go back to the single oscillator, single atom. Okay, and let's write the work, the elementary work done by a force F. So you remember the structure, you have an atom with an electron oscillating around the nucleus. So let's calculate the work, the elementary work, which I will call du. Okay. Due to the force F on the displacement dx of the electron. So du is equal simply to F times dx. Okay, so F is the external force, and dx is the displacement, elementary displacement of the electron. Okay, very simple. So in our case, what is F? So F comes from the electric field. Okay, so it's the charge times the field. So it's minus E times E, the field E of t times dx. Okay. And if I write now du over dt, which is the rate at which the power is delivered by the field to the classical oscillator, du over dt. Okay, so let me write it. It's the rate of power transfer from the field E to the oscillator. So this is exactly minus E epsilon of t. So dx over dt. This is simply velocity, or you can write it in terms of the dipolar moment, which gives you epsilon of t d mu over dt d mu. Okay, where mu is the dipole moment. Okay, that's for one single oscillator. Now, if I consider a collection of atoms, collection of oscillator. So I'm going to sum this rate here. I'm going to sum that over all the atoms. So I call that the average. So du, I call that dua over dt. dua over dt is the average power, average power. This is per unit volume, delivered again by the field to the atoms, to the collection of atoms. So dua over dt will be just a sum. So 1 over v for the normalization, 1 over v, sum from 0 to n, the density number of atoms times the volume, of the derivative of all the dipole moments, d mu I over dt. Okay? And this is what we called, last time we called that the polarization, the electric polarization. So it gives you epsilon, I forgot epsilon here, yes, epsilon of t. So it's epsilon of t times p, dp over dt, where p, again, is the electric polarization. Okay? So this is simply the product of the field times the derivative of the polarization. Okay? So we can calculate that actually. What do we know? Let's put it like that. Let's write the field first as a function of time in the phasor notation. So epsilon of t is real part e exponential I omega t plus e star exponential minus omega t. So that's the complex notation for the field. This is a real quantity. This is, each term here is a complex quantity. And we have the same thing for the polarization. P of t is equal to 1/2 P exponential minus omega t plus P conjugate exponential minus I omega t. Okay? So if I just write this expression, if I use this notation here, and if you remember that there is a relation between P and E, P of omega is epsilon chi of omega times epsilon times E of omega. Okay, there's a relation, the transfer relation between P and E. Okay, so now I have everything, and I want to replace that here. So you see what you'll have. When you do the derivative of P here, you'll have I omega will go out. I mean, there will be I omega when you derive this expression, and you will have P exponential I minus omega t minus P conjugate. Okay. So you'll have, when you do the product here, you'll have terms here with I omega t and I omega t. It will give you 2 omega t or minus 2 omega t, and some term they will cancel. You get constant term, omega t and minus omega t will cancel. Okay. So if we average this quantity here over time, if I take the average, any oscillating term on average will be 0. So I just keep the constant term. Okay. So if I consider the time average power, I have dUA over dt average over time is equal to what? So to this expression here. So what are the terms that will be left here? So there is a I omega in front because of the derivative. There is 1 over 2, 1 over 2 is over 4. Okay, times. I will have these terms that will survive because you have I omega t minus I omega t, so it's constant. So this will survive after averaging over time. So you have P E star, okay, and then this cross product here, E times P star, there is a minus in front, so it's minus E P conjugate, okay, and you agree that all the other terms, for instance, this product here will give you an oscillating term at 2 omega, this one also. So on average in time it will go to 0. Okay? When you take a cosine function and you average to over time, it's 0. Plus minus, okay? So that's what you get here. And now if you use the expression of here, P versus E, using chi, remember that chi is a complex function. Chi of omega is, by convention, is chi prime of omega plus I k second of omega. I don't like very much this notation here. It's not a derivative, okay? It means real part and imaginary part, okay? Don't mix up, okay? So if I use this term, this expression here with that here, okay, I give you the final result. It's very easy to replace these two products. What you find is minus 1/2 epsilon omega times chi second of omega times E of omega modulus squared. So we have a very nice expression. So what do you see here? So you see that the power, the average power which is transferred by the field, the incident field, into the system is proportional, okay, to the intensity of the field, that's for sure. And it's proportional here to the imaginary part of chi, of the susceptibility, okay? So you remember this Lorentzian shape, okay? The imaginary part times epsilon, okay, and omega here. Okay? So now you understand that this part is very important. This shape here gives you really the gain of the medium. It tells you how much you can really transfer how much power you can transfer inside the system, depending on the position, the frequency, compared to omega A. Yes?
So what do we need the real part for? What does it represent?
So let's say you have a system with no imaginary part. Okay, what happens is that so your field comes inside the system. Okay, so what it means this is time domain. Okay, we are integrating over time here. So this term, what it says here is that the imaginary part of chi is in phase avec the field with the field and the diatomic population that are in phase. So this is the term which absorb the energy coming from outside. But the real part of chi, the chi prime here, is out of phase with the field. Okay? So it means that the field comes inside the system and it gets out. There can be some interaction, but on average, everything that came in gets out of the system. Okay? So if the chi here would have only a real part, it will mean that the field will just cross the system. It can induce a phase shift. Okay, the field can be shifted in phase, but there is no absorption of the energy from this field inside the system. Okay, I try to give you really the understanding, the physics understanding of what we are doing here. Okay, so here this is really how much you absorb, how much the atomic structure, the collection of atoms will absorb the energy that is crossing through the system. Okay, and it's very nice because we didn't use any complex things. No, I mean this is just a very basic mechanics. Okay, so there is another demonstration that you can look at here, and that's it. We have everything here.
So this is the external electromagnetic field that drives the system?
That
drives the system?
Right, yes, I mean you can look at it as a driving force, or simply the fact that there is an exchange. Okay, it's like it's like driving means actually that the oscillating field is enhancing the oscillation of the atomic system, like the swing. Okay, when you push a swing, okay, the energy that you hold, you put it in the swing. You transfer the energy into the swing that will swing with a stronger amplitude. It will increase if you are in phase with it. If you are out of phase with it, the swing does not move, or it stops, okay? And all the energy that you put in is restituted back to you or outside, okay? So you can write it, actually you can replace omega second here, and I will do it because I want to show you what it looks like. So we have, so let's say, I take this expression here, I will write it here, okay? dUA over dt, average over time, is what? So I replace, if you remember the expression for chi second here, it's 3, the famous 3 star over 8 pi squared. 8 because there is a 2 here, so 4 pi squared becomes 8 pi squared times epsilon omega, here, epsilon omega, And then the terms in chi square is lambda L cube times gamma radiative, okay, over delta omega A. So this term you will see it many times, times the field here, E of omega modulus square, and the Lorentzian shape, 1 over 1 plus 2, so that's for the 2 omega minus omega A. This is the delta x, delta omega A. Okay. Sorry, the square is here. Okay. And there is one term missing here. What is the term missing in this expression? Check your notes.
N.
Right, n. It's not n because we changed n into delta n, if you remember. So you're right, delta n is missing, so I have to multiply here by delta n. Okay, so I did it on purpose because here what you see is that the energy transfer is proportional to delta n. So that's what I was saying at the beginning to introduce this chapter. Okay, there is a transfer of energy which is proportional to delta n. Okay, and the question is what the atoms are going to do with this energy that they receive. Okay. Okay. So let's consider an atomic system. Okay, in terms from the quantum point of view. Okay. What is the energy if you consider an atom with multi-level atom? Okay. What is the energy of atoms like that? So the energy is just the energy of a given level times the population in that level, and then you sum over all the levels. Okay? So, I want to make some place here. So, energy stored by atoms. So if you consider that from the quantum point of view, you write that the energy U of t is the sum over all the level from 1 to, let's say, to m level of the population of each level, nj of t, times I of g. Okay? This is a quantum point of view, okay? Here I'm switching to quantum point of view. Okay. So in that case, if you think about the energy of the system, I mean the energy is fixed. There is no way you can I mean, yes, you can change it here, but let's say the total number, the sum from 1 to n of the nj of t, this is a constant, okay? The population is constant, the number of atoms, of electrons inside the system is fixed for a given atom, okay? So the population is conserved here. So if you look at this expression, you say, how can I transfer the energy to the system? How can the system can store this energy? And you see that the only way to do that is how? How can you increase U of t here?
To change the population of the energy levels.
So you cannot change the total population.
No, but all the population will be in the higher energy.
So you have to redistribute the population among the different levels, okay? So some level will lose, will reduce population, and other level they will increase population. So the only way to modify here to increase, for instance, the energy stored inside the system will be by having an exchange of population, a transfer of population from one level to another level. Okay. So how can I write that? So U of t increase if population distribution is modified. Okay. So, just to conclude here, you see that on one side, the applied field, the external field, has two actions. We have two actions here. One action is to induce a microscopic polarization inside the system, this P of T, okay, that we have here. And this polarization is proportional to delta n. And on the other hand, because you bring energy inside the system, you also modify the population distribution inside the system. Okay, so on one side you have induced polarization, which is proportional to delta n. Okay, and on the other side, you have a change in quantum levels, population. And J. Okay. So you see here, this effect here is directly related to the CEO model, the classical oscillator model, and this part here is more the quantum description of the problem. So now we are going to bring these two pictures together. And this is very easy. I can write here delta n is n1 minus n2. Okay. In case you have a degeneracy, it will be G1. G1. I forgot if it's G1 or G2. Over G1 in front of it, okay. Anyway, so if you write it like that, then we can rewrite completely the transfer of power, the power transferred here on average over time, into two terms. One term will be in front of n1 minus a constant time n2. Okay? So that will remind you something. Just want to erase here. Can I erase here? Okay. So I can rewrite this expression here like that. This is equal to W12 times N1 times the quantum of energy h bar omega A, sorry, minus W21 times n2 h bar omega a. You remember that from the first class? Okay. So when you have a field incident inside an atomic structure, you stimulate transition. Okay. One transition, this one here is an upward transition. You bring atoms from lower energy to higher energy. Okay. You inject energy which is absorbed by the system by transfer of population from lower level to higher levels. And this term here describes the stimulated emission. That means that part of the energy stored inside the system is released. So that's why you have a minus here. And this is the downward transition. So I usually write it like that. This one like that. So you have stimulated absorption here, and here you have stimulated emission. Okay. So, did you catch the point here? Okay, we have, until now, we have this description of a transfer of energy into a system by bringing, inducing polarization. Okay, and this induced polarization is proportional to delta N. But we would like to have a description, a quantum description of the system, which is more a transfer from one level to another. So just by using this expression here, okay, I can rewrite it in terms of transfer from low level to higher level and transfer from high level to lower levels. And I completely describe here how the energy is transferred into the structure by simply a change, a redistribution of the levels inside the system. Is it clear? You can say no. That's okay? I think it's very nice. I mean, you really see how we make like a kind of connection, a direct connection between the classical model and the quantum model. And yes, okay, you have to add this term here to put some kind of quantum of energy that will go into the constant. Okay, but you have really a quantum description of the problem. And here, if I want to put names, so omega W12 is the probability to make a stimulated absorption. Stimulated absorption of the quantum of energy h bar omega a. Okay, and W21, I'm not going to write it, but W21 is the probability to make a stimulated emission of a quantum of energy h bar omega a. Okay?
But where is the threshold? There is no threshold in this formula.
We are not talking yet of laser, of threshold is when you will consider gain, what I disconnect here, and you will compare that to the loss of your system. Okay? That's what you mean, the threshold of the laser? We are not yet at that level, but we'll get it soon. That's what
yeah.
That's what you mentioned. No, but this is very useful. Remember, we wrote the rate equation in the first class. So now we know where it comes from. We have expression for this W12 and W21. I can write them here, by the way. Let's write this expression. So W1. So you remember, by the way, that they are equal. In principle, they are equal. W12 is equal to W21. The probability to have stimulated absorption is equal to the probability to have stimulated emission, is equal to 3 over A pi squared times epsilon lambda A cube times gamma radiative times the field modulus square and divided by h bar. The omega disappears. H bar delta omega A times the bell shape of the Lorentzian, 1 over 1 plus 2 omega minus omega A over delta omega A squared. Okay? So it's nice. We are describing here the stimulated transition, and we know exactly, we can write exactly the expression for the probability for this transition. You should be excited about that. Right? No, it's nice. I mean, we have all the terms here, and all those terms, those are terms that you can measure. We have the field, we can measure that, we can measure that. I mean, it's a complete expression. You see that there is a dependence on the frequency here, on omega. In the future course, this term will be, in general, it will be ignored, okay? I mean, either omega is close to omega A, so this is 1, or omega is far from omega A, and there is no transition. So you'll see there will be no frequency dependent of W12 and W21, but we can leave it like that for the moment. You see that's very important. So this term is proportional to E square, okay? So it's proportional to the intensity of the incident field. W12 and W21 are equal. Actually, this is true when you have a two-level system, or between two levels. If we have now this small complication of degeneracy here, if we have this term here, then there is a slight change. It will be more like G1, if I make it right, G1 omega W12 is equal to G2 W21. Okay, that's the reason why I always keep the notation. I differentiate the two terms. Actually, they are equal in general, but when it degenerates, then the equality is like that. You have to put the weight, the number of modes, of states in each level, in each energy level. And if you know a little bit about that, this is, you know, this is called. This is called the Fermi golden rule. Fermi golden rule. Okay, and the Fermi golden rule describes the probability of transition W12 here. And this is derived using time-dependent perturbation theory, so it's more complicated than, I mean, the derivation is much more complicated than what we did here, which is quite straightforward. Is there anything to say more? I think that's it. In the first class, I think we called that K. No, it was K. We'll call it. Yeah. When I say, by the way, just.
Yeah.
Yeah, it was. Yeah. when I say probability here, it's always a probability per unit time and per atom. I don't want everything to be correct. And that's it. Now we can really start to write the rate equation. I don't think in the first class we didn't give the expression for this case. There was no. I don't think I gave it. If I gave it, it was without demonstration. Now we have a complete demonstration of that expression.
Yeah, we didn't give it.
Okay, so now it will be very easy. We are going to play the game. We are going to describe the rate equation. We start with two-level atomic system. Then I was planning that it's going to be difficult. I was planning to do also the four-level atomic system, and the three. And we are going just to write the equation like in the first class. We still have some time. So this is 2 here. I really try to simplify the course in comparison to the book from the Sigma. I try to make it simple and clear in terms of interpretation. I hope it helps. There is a long discussion in the book that I'm skipping now, which is about the fact that actually you can describe this description in terms of energy exchange and stimulated transition. You can see the system itself, the atomic system, as interacting with the rest of the world. Okay, so it can interact with an external field. It can also interact with the radiation that are present everywhere, and the black body radiation, for instance. It can interact with the rest of the world by non-radiative interaction. But all these interactions, in principle, you could write them as a stimulated transition. And you can show that, for instance, if you consider the lifetime, the decay of the atomic structure of the transition, okay, the decay itself is an interaction with the outside of the world, but only in one direction. Actually, there is no stimulated absorption. There is only stimulated emission. It is stimulated. Actually, it's not stimulated. This is, we call that spontaneous emission, but it's an interaction with the rest of the world. So there is a few pages about that. It's nice for the idea, for the principle, but I don't want to complicate the picture. I think we have everything here to start to write the equation. So let's consider the two-level atom. Simply, I put it like that. I have level 1 here and level 2 here. And we have the transition here, which is given by W12, and the transition in the other direction, which is given by W21. Okay, so if I write the rate equation, I have, so this is, actually, my representation is like that, let's say. This is the level 1, level 2, and here this is the population. So it's N1, N2. Okay. So I have dN1 over dt. So the rate of increase of N1, which is the opposite of the increase rate of N2, is equal to, so actually N1 is losing population through this process, through the stimulated process from level, for the upward process from level 1 to level 2. So we have minus W12 times N1, so it's N1 of T, okay. It gains population for the other process. It will be 2,1 times N2, okay, N2 of T, okay. And then there is the natural decay due to the relaxation of the transition, which is given by gamma 2,1 times N2 of T. Okay, so here we have all the element of the, yeah.
So the radiation that gets out from one level, we are considering it to go to the other level?
Yeah, yeah. So let's we consider a system here which is conservative. Let's say that we have N1 of T plus N2 of T. Let's say it's a constant. Okay. We have conservation of population. And then you can write the population difference, delta N of T is equal to, by definition, N1 of T minus N2 of T. Okay. And so we have a system of two equations here for N1 and N2. I just want to rewrite this system here for delta N. Okay, so I would like to have a differential equation for the population difference, not for N1 and N2. Okay, and to do that, I need to do a few things. First, we know that W12 is equal to W21. Okay, so that's easy. We can express N1 in terms of delta N. N1 is delta N like that, then delta N of T, so it's N1 minus A2 plus, I can write it like that. And okay, I want to write it in terms of N here. I want this term and this term, okay? So plus N. I want to remove completely N1 and N2, okay? So it's N over 2, so it's delta N over 2. You agree with me? So delta N is N1 minus N2 over 2 plus N1 plus N2 over 2, okay? So if I make the sum, I get that N1. You agree? I do the same for N2. N2 is equal to delta N of T over 2 minus N over 2. Okay, so I know how to change my variables from N1, N2 into delta N, and N is not a variable, N is a constant, okay? So I can rewrite things like that, and I can replace that in this equation here, and I get the following. I get delta D of delta N over dt is equal to, so what do we have? I have minus W12 from here, minus W12 plus W21 times delta N of T minus gamma 21 times N2. N2 is delta N of T minus N. Okay, so I just rewrite what is here, but this time for delta N. Yeah, and the two is due to the fact that here, this term is twice this term here. Okay? The derivative of delta n is twice the derivative of n1, so the of 1/2 here disappears, and I get finally I get minus 2 W12 because it's the same times delta n of t minus delta n of t minus what I can, okay, let me take it like that, and over 2, 1, 2. Okay, gamma to 1, gamma to 1, sorry, I wrote it, gamma to 1. So why do I write it like that? Let me write, let's assume that, so this is the differential equation for delta n, okay? Let's say that at time t equals 0, delta n is delta n0, okay? And actually delta n0 is quite close to n itself. N is the sum. N is the sum. If you assume that at t equals 0, most of the population will be in level 1. Okay, so this is just for notation. I just say that this is roughly n. Okay, so I can just put delta n0 here. I just assume that at the beginning most of the population is on the ground level. Okay. So I have two terms here. So I want to interpret this differential equation. So if you look at it, what do you see? You see actually two behavior, two dynamics. One due to this term, one due to that term. So let's say that we don't have energy, and we are not injecting any energy. So let's say W12 is 0, no external field. Okay, so we have this term here. What type of equation is that? dN over dt is minus this term. Okay, it's an exponential decay toward what?
Hmm?
Of what? I mean, of
Spontaneous,
Yes.
spontaneous emission?
No, I'm just saying. Okay, this is a decay, but toward what? Delta n goes to what? To n or to what I call delta n0.
Yeah.
Okay. Actually, it's a differential equation for delta n minus delta n0, and you have exponential decay to that value. So it goes to 0. The difference goes to 0. So that means that delta n goes to delta n0. Okay. So this term tells you what? It tells you that the population difference goes back naturally to the initial value delta n0. Okay. So there is a relaxation. So if you excite the system, it will relax naturally back to the initial population difference delta n0. Okay. So that's for this term. What about this term here? What does it tell you?
Linear.
Hmm?
It's linearly.
No. It's look. If I ignore this term, okay. So dN over dt is a constant time delta n. Okay. So it's again an exponential decay. Okay. But this time, what time of relaxation do you have here? To what do you relax? You relax to delta n equals 0. Okay. So if you have a term like here, a non-zero term here, if you have some energy injected inside the system, what the field, the external field, is doing is it forces the system to relax to the situation where n1 is equal to n2. Okay, and actually you cannot do better than that. In a two-level atom, you cannot do better than having n2 equal to n1. You cannot have a population inversion. We'll see that later. In a two-level structure, there is no population inversion. The best you can do, and you see it here, is to go down to delta n equals 0, meaning the n1 equal n2. Okay? So this term here, due to the external field, show relaxation to the situation where n1 equal n2, population difference 0, and this term shows relaxation on this time scale to a population difference, which is the initial population difference, delta n0. Okay? So we have like two mechanisms in competition. One is the natural relaxation of the system back to the initial state, okay? And the other one, which is the forced term by the field, is a relaxation to delta n equals 0, where you have actually you minimize delta n. That means that you maximize the population in n2, and at maximum n2 is n1 is equal to n1. You can have as many atoms at level n2 than at level n1. Okay.
N0 is all the population.
Let's say that delta n0. Let's say that you start with everything at the level 0, at level 1. Okay, all the population at level 1 and almost nothing at level 2.
So this exponent is not decaying because n0 is bigger than n2.
No, let's say the system is excited. Okay. Let's say you excite your atom with a lot of atom in the higher level, okay, and you let the system relax by itself. What will happen is that it will relax back to the initial condition. Okay. This is the case where you don't have any external field. If you have an external field, the system will decay because it cannot stay in this unstable situation where n2 is larger than n1. It will go down to a situation where n1 and n2 are equal. Okay, that's the best that you can accomplish here if you excite the system externally. Okay, so actually what it says is that if you have this process, this stimulated process here, what will happen is that at maximum you will reduce 1 and you will increase 2 so that they will be equal. You will have equal probability transition upward and downward in the system. So we can solve this equation in the simple case where we reach the steady state. Okay, that's always the way to do that. So if I write the steady state solution, d of delta n over dt equals 0. Okay, so what do we get here? We get that delta n at steady state, I call that delta n SS at steady state, is equal to delta n0 over 1 plus 2 W12 tau 12. Or you can rewrite it like that. Delta n0 is 1 plus W12 over W saturation, or W sat, or 1 over tau 12 to 1. I don't know why I want it. It's to 1. Okay. So if you draw this curve here, you get something like that as a function of the energy of the intensity of the external field as a function of W12 here, what you get is that if there is no external field for omega W12 equals 0, okay, the steady state will be what? It will be delta n 0. Okay, it will be here, so this is delta n. This will be delta n 0 here. Okay. As you increase the intensity of the incident field, the steady state goes down like that to reach the value of 0 for delta n. You see? So this is interesting. This is called saturation of it, in fact. And if you realize that, okay, this equation is for delta n, okay, for the population inversion. But if you realize, for instance, that the absorption or the gain inside the system is proportional to delta n, so you will have the same type of expression for the absorption. I can write it like that. Let's say, let's call that for the absorption, for instance, absorption. Alpha, which is proportional to delta n, so alpha will be written like that, alpha 0 over 1 plus intensity of the incident field over E saturation. So this I don't remember if we saw this expression in the first class, but this is the saturation of the absorption as a function of the incident field. It means what? It's very interesting because you see, so for 0 intensity, you have alpha 0. Okay, this is the absorption of your medium. As you increase the intensity that crosses the system, what happens? You saturate the transition, and this term increases, and alpha goes to 0. You know what this is called? This is called saturable absorber. A saturable absorber. And this is used in lasers. So you understand the story. You have, let's say you have two level atom like that, okay? When you have light coming inside the system, the light will be absorbed, okay? That means that the atom will transit from the lower level to the higher level. This is absorption, okay? Nothing, I mean, the photons that come in do not come out. They are absorbed by the system, okay? But if you increase intensity, there will be a point, you will reach a point where the number of atoms in the lower level and the higher level are equal, okay? And then you are saturated. You cannot bring more energy inside the system. So the photons that come, they don't see any way to transfer their energy into the atomic structure, so they will cross the system. And the system becomes transparent, okay? So that's what you see here, the absorption. When E goes to higher value, the absorption goes to 0. So you design a material which is opaque, which absorbs the light at low intensity, but at higher intensity it becomes transparent. You see? So this is called the saturable absorber, and this is very useful in lasers. If you want to make what we call a Q-switch laser, we want to have a laser with very short pulse. So what we do is that we introduce, and this is done in the lab, in the quantum optics lab. We are going to introduce a saturable absorber inside the cavity, and what you see is that if the energy inside the laser is too weak, it's not strong enough, the system is blocking actually the laser. So actually, the saturable absorber increases the loss inside the cavity. So So if it increases the loss inside the cavity, it means that the threshold of your laser is very high. Okay, but as you increase, as the intensity is increased inside the cavity, then there is a point where suddenly the absorber will not absorb anymore. It will be completely saturated, so it will become transparent, and suddenly the threshold of your laser drops. Okay, so you start with a laser which has a very high threshold, so the system is pump, okay, until it reaches this level when the medium becomes transparent, and the threshold goes down rapidly. Okay, and then you end up with a system with a lot of energy that it has to release. Okay, so it gives you a very strong pulse, a short pulse with a lot of energy coming out of the laser. And that's how you make a Q-switch laser, which is a pulse laser with very high energy. But this can be used for other things, and it's not only for lasers. And this is the idea. You have two levels. First, you absorb because the energy is transferred into the atom by redistributing the population. But once you reach delta n equals 0, means n1 equals n2, no more photon can be absorbed by the medium. So if it's not absorbed, the system is transparent. And that's how you do that.
They can't absorb anymore because they're in their highest energy level?
Because in the steady state, we reach the maximum you can have, which is n2 equal to n1. So they cannot be absorbed anymore. Okay, it's
What
like
is
the level 2 is not completely full, okay, but the system cannot accept more. That's the characteristic of a two-level atom. You cannot have more atom in the higher level than in the lower level. Okay, and that's the reason why you cannot make a laser with a two-level atom. There is no way you can make a laser because you cannot reach population inversion. At maximum, the time equals 0. Okay. So we see that you have to go to a 3-level or 4-level atom to be able to inverse population and get larger population in the upper level of the transition compared to the population in the lower level of the transition. Okay? Maybe no, that I will do that for the next one. What time is it? Okay, I'm done. I just want to give you, so that's the steady state solution. What will be the full solution, the complete solution? So complete solution, that means that you start from an initial value, okay, and you look at how the system evolved in time, you look at the transient in time. So if I write the solution here, so it's not a complicated equation, differential equation. So you can write the full solution. Transient solution, and you write it like that. So let's say that at t equal t0, you start from delta n of t0. Okay, and at that time, you turn on the field, the external field. At constant intensity, okay, so E squared or W12, okay. So the solution will be like that. Delta n of t will be equal to delta n. So you have to put the solution for the steady state solution plus a particular solution of the complete equation. So it's delta n steady state plus delta n at t0 minus delta n steady state and exponential of minus 2, 1, W12 plus 1 over tau 1, 1, 2 T minus T0. Sorry. Okay. So that's the full expression. So if you replace, if let's say W12 is 0, then you recover that delta n of t will go down to delta n 0. So if I plot it, I want to make a last plot. Okay. So what do you have here? You have delta n of t versus time. This is time, okay? So we start at delta n of t0, delta n of t0, so this is t0. Okay. So if W12 is equal to 0, this will decay to delta n 0. So delta n 0 is here. A slow decay like that. This is the case of W12 equals 0. And if you increase now the intensity of the external field, you will have a faster decay going to lower values. This is W12. So actually they plot it like that. This is 2 times T1. I forgot to define T1. It's 2, 1, 2, 2 equals 0. So the same value for 0.5, then it goes down for 1, 4. Okay, so this is the steady state solution for large time, and this is the transient, starting from an initial value. And you see how the population will evolve as a function of time when you force the system with a given field, W12, with different value of this field. Okay. Okay. I think we should stop now. Yeah. Next time we'll discuss the 3-level atomic structure, the 4-level atomic structure, and then you will see it's richer system, and then we'll be able to have lasing. That means that you can pump the system, you can excite the system to have population inversion and to have amplification. Actually, you want to have amplification of the light that comes inside the system. Any question? I try to clarify things. I really wanted to do 2 chapters today, but I did only one, but it's good to take time and to explain. Okay, all these expressions, all these calculations, really to bring more understanding in the physics of the laser. So here, in that case, there is no lasing, but there is the saturation effect. It's very important to understand the saturation effect. And on top of that, it is very useful. And we'll see next time what happens when you have population inversion in the system. Okay, thanks a lot.
Thank you.